Alright, hell yeah. So most textbooks have the rules for exponents. But guess what? This problem on the internet tripped me up. Because it involves a tower. And nowhere in these rules of exponents do they actually show you a tower. So we have a number to a power to a power. Now this is equal to, this is where you put the parentheses. You know what I mean? You have to work from the top down. And so this is not equal to this number to a power and then parentheses that number to a power. So because in our one of the rules says that, hey, if you do have a number to a power and then you do have parentheses and you're going to take that to another power, then you can just multiply. And so what happened was, based on that rule, I just saw this -2 and a -1, and so I made the mistake of being like, alright, hell yeah, this is in the parentheses, let's do that first. So this is not 9 to the -2 times -1. It's not 9 squared. So what we have to do is add our own parentheses based on, the rules of towers. And so, and the reason, I guess the main reason to not get confused, this is a good one to go over, is like a good thing to think about is that towers are huge numbers, or can be, you know what I mean? And these are just like, hey, I just have like maybe, this just becomes maybe a normal number to handle, and then we're just, maybe squaring it, cubing it. That's going to be still a normal number. But anytime you get a tower, it could be huge. So let's compare 10 to the 10 to the 10. Compared to 10 to the 10 and then to the 10. Alright, so, and it's not so obvious, like, which one is incredibly huge and which one isn't. So, I think a good strategy, well, let's do this. This is 10 to the 10. So that's going to be 10 times 10 times 10 times 10. And you're going to have that 10 times. Alright, hell yeah, I had to pause the video because sometimes, yeah, it's a little bit mind-numbing. But hell yeah, if I have 10 times, and we should even write this out. I mean, that's 5, 6, 7, 8, 9, 10. If you're able to, you know what I mean? If it's less than 20 digits, you know what I mean? Start writing them out. Even if you have Avogadro's number, 6 times 10 to the 22. What is this? You know what I mean? This is 6 with 22 zeros. You know what I mean? And that's going to be the number. And you should be able to write those out. So, what is this 10 to the 10? Well, it's 1 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hell yeah. And you should be able to write, so if it's you could write 22 zeros. Is it 10 to the 22? Is it 10 to the 23? I kind of forget. 6.02 times 10 to the 23. There you go. Alright, so this is going to be 10 to the 10, and then we have it to the 10. So we're going to have this 10 times. That means we're going to have 1 with 100 zeros. Okay, so I could still write that. You know what I mean? 1, 2, 3. I could just do them as dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I could do that 10 times. You know what I mean? That's about 4. So you get the gist. You could actually write that number on this page. So now let's take a look at this one. Because we have this tower, we have to do this first. And 10 to the 10, well, that's going to be this 1 with 10 zeros. So I can even write that out. You know what I mean? 1 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Make sure I got them all. And I think I got one more. So we have, no, that's 10 zeros. We got 9 zeros, 10 zeros. All right, so now what is this? Well, this is 10. So what number is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this would be a million. This would be 10 billion. Cool. And so we're going to have 10 billion times. So now, So now if I get the gist, like I can't even, wait, I have to do this 10 billion times? And you know what I mean? Can you even like put dots on a page? Can you put 1,000,000 dots? You know, if you did this and filled dots on pages, it would probably take you a week. You know what I mean? Because you'd have to take breaks and stuff, and you'd just get bored. So this just says, hey, do this 10 billion times. You know, 10 billion ain't even, it's not even a big number. But the fact that I have to actually write tens a billion times, that means that this number is 1 with 10 billion. And you know, I might have made a mistake. But there you go. We have 10 billion zeros after this. Now that I cannot write. This I could write 10 to the 10 to the 10. What was that? Just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 zeros, and I just got to do 100 zeros. Okay, yeah. I mean, we could. What was that? That number is going to be that long. This number is. I mean, yeah, and you should like. I remember, well, in grade school, there was they printed out periods on a page, and it was just like a whole stack. It was 1,000,000, so it was 1,000,000 dots printed out, and you could start counting them. So that would be that number. So that just shows you towers can be big numbers. Now, if these numbers are, you know, small, or 0.9 to the 0.9 to the 0.9, it might be the other way. They might be incredibly small numbers, or but hell yeah. So towers in general are typically going to be used for very big numbers. This is the classic case that comes up a lot. So when you see this problem on the internet, you're like, hell yeah, this looks a little bit tricky. Alright, so let's do it. You know what I mean? And we're going to have -2 to the -1. Now I'm gonna even use this, because you can use these. I'm gonna pull up all the rules for exponents. So here's the one that we're gonna be using for that I'm gonna be using in this video, and it's good to maybe even print these backwards. You know what I mean? Because if I have a case like this, I can get to here. But what that also means is that if I have a case of a number, you know, to some you know, if I have a to the 6, well, I can break up 6 into a to the 3 times 2. And so that can be a to the 3, a to the 2. So that's kind of what we have here. Alright, booyah. So the same thing, I do this with negatives, and this is going to be really helpful. We got -2 to the -1, and you could just say to the 1. Alright, so here's the exponent rule for negative exponents. So a number to the -m is going to be 1 divided by that number to that exponent. But if you break it up, what we can do is we can still use this process. And this is probably really redundant. But what this is going to say is like, hey, I'm going to take, and I can do these. The cool thing about this process, that I should say, is that a to the m to the n, sure, that's going to be a to the m times n, but these two things can be in any order, because this could be a to the m times m. You can switch the order of those. And so this is going to be a to the n times m. And so this way you can do either of these in whatever order you want. So I can take -2 to the 1. Cool. And then I can take that to the -1. But yeah, super redundant to break this up. But it's going to be useful if we break up -2. -2 is going to be -1 times 2. Okay, so this -1 is just going to take this number, and it's going to put it 1 divided by -2, which is going to be -1/2. So now we're going to have 9 to the -1/2. Cool. And then -3. Alright, so what this says, there's 3 things going on here, so we can even break this up. This is going to be 9 9 to the negative 1, and then, or I guess maybe just two things, and then 1/2. This 1/2 is going to be the square root of 9. So we're going to have square root of 9, and then we're going to take that to the negative 1. You could have done it the other way. You could have done it 1 to the 9, and then we're going to take the square root of that. So that would be 1 to the 9, and we can take the square root of that. Square root of 1 up top, square root of 9 on the bottom, and so it's going to be 1, 3. And so, sweet. So square root of 9 is 3. 3 to the negative 1 is this, 1 divided by this number. Hell yeah. Alright, so so that's going to be what we have. What was that? Yeah. 1/3 was going to be this number right there. So now we have get another note card out. So now we have 1/3 to the negative 3. Alright, I'm going to break this up. 1/3 to the negative 1. And I can do that first. And this is 1/3 to the negative 1 times 3. So basically, it just says that I can break this up as 1/3 to the negative 1. And do that first to the third. Or I can say this is 1/3 cubed. And then take that to the negative 1. You know what I mean? So if we do it this way, we're going to cube the top, cube the bottom. Top is just 1. We're going to have 27. And then we're going to take that and invert it. Cool. And we're going to get 27. So that's the answer. And this, we're going to invert this number. So 3 divided by 1. And we're going to cube it. So we have 3 cubed divided by 1 cubed. This is going to be 27 as well. Alright, hell yeah. So that was just a little video. That was pretty rough. But anyway, I got hung up on this one. And so I think the take-home point for this video was like, hey, this is a tower. And we need to start at the top. And the reason you would do so is because the numbers are for sure going to get crazy huge. If they're kind of normal numbers and you're stacking those towers. Where, if you do it this way, you know, start from the bottom, hey, you might have a pretty big number, but a pretty big number squared is nothing compared to 2 to that really big number. If you switch the order of those, it's just like, yep, you know what I mean? So this would be the case if you had 2 to the 2 to the 2 to the 2 to the 2, you know what I mean? This can get big real fast. This is not just a big number squared. It's going to be 2 to a hell of a big number. Huge difference between those two. So, and it's, you know, even just talking your way through it, it's not super obvious. I mean, just because it's the swipe of a pen. You know what I mean? Where, like, it's just the order that you would do things, and so it's kind of visually difficult to see, you know, even between these two. Which one is fairly large, and which one is enormous. Alright, so hell yeah. So I think I'm done with this one. Thanks for joining me, and that's a video.